biggest misconceptions about special relativity, at least in these times, is that special relativity cannot adequately explain acceleration and that you need general relativity to do that for some reason. In fact, that is not true at all. So in today's video, what we're going to do is derive an expression for the velocity as a function of time for an object undergoing a constant force and acceleration. So what we're going to start off with is the basic fact from special relativity that the momentum equals gamma mv, where gamma equals 1 over root 1 minus v squared on c squared. And that gamma factor is added in special relativity, and it's approximately true in the classical limit that it equals mv because gamma is fairly close to 1. And now that we have that, what we want to do is remember that force is defined as the derivative of momentum with respect to time, and subbing in that definition we have up there, we end up with F equals d on dt gamma mv, and then taking the m out of the derivative because it's a constant, we end up with m d on dt gamma v equals the force. Now, classically, we know that an object undergoing a constant force, F naught, will be the expansion of that, the expression in total on the right hand side will be F naught equals m a naught, and you can see both sides they're constants because I put in the naught subscript to show that F, the force, is a constant, and same subscript for a, so the acceleration is also constant in this case. Now, as I said earlier, what we want to do is find an expression for the velocity when it's undergoing a constant force, the object is. So we just assume that F on the left-hand side of this equation is a constant. And I'm gonna drop the naught subscript because it becomes too much of a pain to write as the video goes on. So now what we want to do is we want to integrate both sides. And I neglected to mention that we're doing this for a case where an object accelerates from rest. So any integration constants, we're just going to set them to 0. So if you integrate both sides of this equation, you end up with ft, f times t, integrate with respect to time, you end up with f times t equals m, or gamma, mv. And we want to divide both sides by m. ft on m equals gamma v. So what do we do now? Well, if we look back at our definition of gamma, the gamma factor before, remember that that's 1 over root 1 minus v squared on c squared. So we just sub that in. Then we get ft on m equals v on root 1 minus v squared on c squared. So we're in a bit of a conundrum now because we've got v on this side over here, but it's also got v in the denominator of the fraction. So one way we can get around this is to square both sides. So you end up with this, f squared t squared and m squared equals v squared on 1 minus v squared on c squared. And now what we want to do is multiply both sides by 1 minus v squared on c squared. You end up with f squared t squared on m squared minus f squared t squared on m squared v squared on c squared equals v squared. Then we get both terms with v squared on the same side. And once we end up with both v squared terms on the same side, we can factor out the v squared. So we end up with v squared times 1 plus f squared t squared on m squared c squared. And we're basically there. So what we do now is divide both sides by 1 plus f squared t squared on m squared c squared. And then you end up with v squared equals f squared t squared on m squared, all divided by 1 plus f squared t squared on m squared c squared. And then take the square root, you end up with ft on m, and in order to simplify this, I'll just bring the m to the bottom on the denominator, times root 1 plus f squared t squared and c squared. And then, since you could rewrite m as root m squared, you end up with our final expression, v equals ft on root m squared plus, oh, I put the m squared here, m squared plus f squared t squared on c squared. And you can see the m cancelled out with the m squared cancelled out the m squared on f squared t squared on c squared. So we've got this final expression right here. Now that we've got a final expression for the velocity as a function of time, we want to tinker with the equation a bit to see what interesting properties it will have. And right off the bat, one of the interesting properties you'll see is that if you take the derivative of it with respect to time, which classically, or just in general, we know as the acceleration, as a derivative of velocity with respect to time, you will see that that is not equal to a constant. The derivative of this equation is not a constant. So even though we assumed at the start of this that, or rather we expected at the start of this, that we would get a similar classical behavior where we would have mass times constant acceleration for the force, for a constant force, in fact, in this case, we cannot have a constant acceleration. And this is because you cannot exceed the speed of light in special relativity. So what will actually happen is you will asymptotically approach the speed of light. You'll get closer and closer, but you never actually reach it in a purely mathematical sense. Realistically, it's close enough to the speed of light that it wouldn't really matter, but it is not exactly the speed of light, which is about 3 times 10 to the 8 meters seconds squared. And another interesting thing is that we can sort of surmise, or just sort of have a bit of a reason to assume, after looking at this, that if you have mass equal to 0, then an object will move at the speed of light, or perhaps that light itself has 0 rest mass. And we can verify this by setting mass equal to 0 in the equation, where you end up with ft on root f squared t squared on c squared. And obviously root f squared t squared on c squared is just ft on c, so you have ft divided by ft on c, which is just equal to ft times c on ft, which is just equal to c, the speed of light. And I must stress that this is just a limit of the equation as the mass approaches 0, because when we defined a momentum that we used to define the force, we defined it as gamma mv, where m is the rest mass. So our derivation of this function for the velocity assumed that the particle, or whatever was accelerating, had an actual rest mass. So obviously it doesn't really make sense to show this as a proof for light having 0 rest mass, because our equations in the first place assumed that the particle had a rest mass. It's just a limit. So we can guess after looking at this that light probably has 0 rest mass, and actually in fact that it's extremely likely that light has 0 rest mass, but it's not a proof. That, I assume, is in the domain of particle physicists and all of that. I haven't looked too deep into quantum field theory, but I'm sure you guys can tell me about that in the comment section. Anyway, now that we've done that, I think that's a wrap for the video. So thanks for watching, guys. If you have any meaningful criticisms or just calling me a shit cunt or anything like that in the comment section, I'm all up for it. So let me know. Thanks.